Hello, in today's video we're going to be covering section 7.1 on exponential functions. So we're going to be identifying exponential functions, we're going to be writing equations for exponential functions, and then towards the end of our section we're going to be going into interest formulas and interest formulas having a base of what we call e. So the first thing I would like to explore is the difference between an exponential function and a linear function. So I have a chart here for us to look at, and I'd like to evaluate the function values for each of these inputs. So f of x is 2 to the power of x. So if I input a 0, 2 to the power of 0 is 1. If I input a 1 for x, 2 to the power of 1 is 2. If I put in a 2 for x, 2 to the power of 2 is 4. If I put in a 3 for x, 2 to the power of 3 is 8. 2 to the power of 4 is 16, 2 to the power of 5 is 32, and 2 to the power of 6 is 64. Now a linear function would just be, for example, 2 times x. So evaluating this linear function for these inputs, 2 times 0 is 0, 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8, 2 times 5 is 10, and 2 times 6 is 12. So while our linear function goes up by a constant rate of 2 from each input to the next, my exponential function, where x is in that power, is not. It does not have a constant rate of change. Here we go up by 1, then we go up by 2, then we go up by 4, then 8, then 16, then 32. So linear functions have a constant rate of change, but exponential functions do not. They grow much more rapidly than linear functions do. Exponentials are going to have the form of a, being a multiplier, multiplied by b, a base, to some power that contains our x. A must be non-zero, and b must be not equal to 1, a positive real number not equal to 1. A is our initial or starting value of a function, and 0a is our vertical intercept or our y-intercept if we're talking x and y axes. B is the growth or decay factor, so how much we are increasing by or decreasing by. We're going to look at the following in example 7.1.1 and determine if these satisfy the conditions that we need. So the first is A, where f of x is equal to a base of 4 to some power containing an x. Now if I write this in the form of f of x equals a times b, my a would be 1, and then I multiply by a b of 4, a base of 4, to a power of 3 times x minus 2. Now we are allowed to have more than just x in our exponent, but x must be in the exponent in order for this to be an exponential function. So a, I'm going to say, does follow the requirements, and it is exponential. B, I have x to the third power. Now, unfortunately, x must be in the exponent in order for this to be exponential, and it is not. So this is not exponential. Our other option is that it could be linear. A linear function would have the form of y equals mx plus b, where the only exponent on x is a 1. This x has an exponent of 3, which means that this is nonlinear either. So in this case, we have neither an exponential nor a linear function. G of x, I have a base of -2 raised to the power of x. So if I write in my a here, a would be 1 multiplied by a base of -2, and x is in the exponent. However, I must have a non-negative base, and in this case my base is a -2. So it doesn't quite satisfy the conditions for exponential. Neither is it linear because it doesn't follow y equals mx plus b. So C, I'm also going to say, is neither. Now D, we do not have any exponents at all, so this will not be exponential, but it could be linear if it can be written as y equals mx plus b. And I can write it as y equals mx plus b. J of x equals, I have a negative 25x and a positive 4. So m is negative 25 and b is 4, which means that this is going to be a linear function. I'd like for you to take a moment to please pause the video and try evaluating exponential functions on your own before I lead you through it. So we are looking for the value of f of 3, which means that they are asking us to replace our x value with 3. So I've got 30 times 2 to the power of 3. F of 3 is equal to 30 times 8, and 30 times 8 is 240. So f of 3 is 240. All I did is I plugged in that 3 to see what the output would be. And for b, g of 2, I'm going to follow a similar procedure. 5 times the base of 3 to the power of 2 plus 1. So g of 2 is 5 times 3 to the power of 3. G of 2 is 5 times 27. G of 2 is going to be 135. So all we did is we plugged in that value of 2 and solved. Example 713. Let's consider two companies, A and B. A has 100 stores and expands by opening 50 new stores per year. So that's a constant rate of change. Every 1 year, we're adding 50 stores. So year 1, we add 50. At the end of the next year, we add 50. The next year, we add 50. The next year, we add 50, which makes this a linear function, and they have written it for us below. Company B has 100 stores and expands by increasing the number of stores by 50% each year. So we start with 100 stores, and then we are increasing by 50%. So this 1 represents the 100% we have. So at the beginning of the next year, we have all the stores. We have 100% of the stores that we had before, plus 50% new stores that we're adding on. And we raise that to the power of x because we repeat this every year. At the end of the next year, we multiply by 150% again. At the end of the next year, we multiply by 150% of what we had, and so on and so forth. So we're going to complete the table and graph both functions on the axes that are provided here. So company A is A of x equals 100 plus 50x. And company B, B of x, is equal to 100 times 1 plus 0.5 to the power of x. Company A, when I plug in a 0, 100 plus 50 times 0 is 100. When I plug in a 1, 100 plus 50 times 1 is 150. When I plug in a 2, I get 200. And when I plug in a 3, I get 300. So on my graph, I'll go ahead and plot 0, 100, 1, 150, 2, 200, 3, and 250, and so on. We've already established that this is a linear equation, so it will be following the graph of a line. Now company B. When I put in a 0, 1 plus 0.5 to the power of 0 is just 1. So 100 times 1 is 100. When I plug in a 1 for x, I have 150. When I plug in a 2 for x, I'm going to have 225. And when I plug in a 3 for x, I've got 100 times 1 plus 0.5 to the power of 3, giving me approximately 337.5. which I'm going to round to 338 because it doesn't make sense for us to have half of a store. So I'm going to go ahead and round to 338. So 0, 100, I'll do this graph in red. So 0, 100, we start at that same place. We did talk about earlier that the 100, or our A value, is our vertical intercept. So we should expect there to be a point on 100 on that y-axis. 1, 150, so we are still matching our graphs. 2, 225, so our graphs at this point start to go away from each other. And 338 would be a little bit between 300 and 350, so right about here. Now I will draw my graph. So connecting these dots, I do see that the first red dot that is not on my linear equation is a lot closer than that second dot is, which tells me that we are growing more quickly and not maintaining a linear pattern. So I'm going to draw my graph to the best of my ability. It's going to look something like this. It grows slowly at first, but then it starts to grow more quickly. We can see that with the difference that we have between our two graphs. And it grows even more quickly as we move on in our graph. So that red graph that I have drawn does demonstrate for us the graph of an exponential function, specifically b of x in this case. We're going to work backwards, and we are going to now find an equation of an exponential function. Remember that equations of exponential functions follow f of x being equal to a, which is our initial value, times b to the power of x. We can have more happening in our exponent, but when we are writing exponential equations, we're going to go ahead and just assume we have x as our exponent. In 2006, 80 deer were introduced into a wildlife refuge. By 2012, the population had grown to 180 deer. The population was growing exponentially. So this is where we know that we're going to be using the f of x equation that I wrote above. Write an algebraic function representing the population n of deer over time in years since 2006. So 2006 is our starting year, which means that the number of deer in 2006 is my initial amount. They tell me that I had 80 deer in 2006. So 80 is my initial. Or, as we've talked about a few times now, that 80 is going to be my value of a. So far, I've gotten f of x is equal to 80 times b to the power of x, just by noticing that my 80 is my initial value and should replace a. So from 2006 with 80 deer, we went to 2012, so 6 years later, and we have 180 deer. So my t is my time in years since 2006. So t here is going to be 6, and the number of deer n is 180. So I'm going to go ahead and change my variables now to the appropriate variables for my equation. The number of deer after t years is 80 times b to the power of t, which is time. So what they have told us is this very specific case where when t is 6, the number of deer is 180. So when I plug in a 6 to my equation, I should be getting 180. And this will allow me to solve for b. So I will divide both sides of my equation by 80 and reduce the best I can. I can divide by 10, and I continue reducing by dividing by 2. So b to the power of 6 is equal to 9 over 4. And then I need to isolate b, so I take the 6th root of the left and the right hand side. So this must be plus or minus the square root, the 6th root of 9 over 4. So b is equal to positive or negative square root of 9 over 4. 6th root of 9 over 4. Now we have talked about how my b must be non-negative, and it may not be 1. So b must be positive 6th root of 9 over 4. So then I can take this and go back to my equation and plug in my value of b, and I am done. N of t is equal to 80 times the 6th root of 9 over 4 to the power of t. And we can use this to predict the number of deer at any time t. I'm going to go ahead and end this video here, and we'll pick up in our next video.